All right, we are going to go over chapter 9, which is over periodic properties of elements. So first thing we want to go ahead and start with is in chapter 9, we want to pick up on quantum numbers where we ended up in chapter 8. So let me do a quick little review of what we did in chapter 8. Second, zoom out. There we go. So we were talking about the different quantum numbers. We had N, which is the principal quantum number, L, angular momentum quantum number, N tells you energy level, L tells you the shape of the orbital, ML tells us the orientation of the orbital. So we went over these three numbers and we can use a series of three numbers to describe an orbital, okay? And then we start talking about how the energy levels were on here, like energy levels going up and 1, 2, 3. So we were speaking of that. And then now I said, there was a fourth quantum number that we want to talk about to describe the electron inside an orbital. Okay, so we'll go ahead and put that in. So this is chapter 9. Long pen. First thing we want to talk about is MS, spin quantum number. And for us, let me go ahead and zoom in, back in. Spin quantum number, we are going to talk about electron spin. And we have spin up and spin down, okay? So we talk about filling electrons, you know, there's rules where they say you can put 2 electrons in an orbital, and then in your electron orbital, when you fill it up, there's spin up and there's spin down. So spin up looks like this, spin up, okay, electron pointing up. So for this guy, it will be plus half for the MS, okay? If it's spin down, then the MS is minus half. And that's how we describe spin up as plus half, spin down minus half. Okay, so that's the last number. We have N, L, ML, and MS. Okay, once you combine all 4 quantum numbers, you can use it to describe any electron on the entire periodic table. So for example, we want to start talking about electron configurations. Okay, so I'm sure you've heard of this. Hydrogen atom. What's the electron configuration? So they start telling you, okay, here's my periodic table. And then on hydrogen here, you start out with 1s, right? And this is 1s1, agreed? So if we go ahead and zoom out a little bit more, we can see the entire periodic table right here. So each orbital has 2 electrons, correct? And then on our quantum number rules there, we learned that there was 1s, and then after 1s, there was 2s, and then 2p, 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 and then 3s, and then 3p, and then we had 3d. Okay, now this is when it starts to mix here. I'll show you guys on the periodic table. So let's go back to this page here and periodic table. So over here, we have, we want to go ahead and fill in our electrons. So this guy here will be 1s1. And then helium will have 2 electrons. We'll fill it as 1s1 first and then 1s2. So the last electron in helium is the one that says 1s2. And then over here, once you run out of space on 1s, you go to 2s. And then here you go, 2s1 is the last electron. This guy would be 2s2 as the last electron. So everyone has their own configuration. But if you look, here's 1s, it's 2 electrons, and then 2s. And then you have 2p, the first 2p, the second 2p, the third 2p, because each one has 2 electrons, okay? So we can keep going on forever, and then we have 3s, 3s1, 3s2, and then we have aluminum, we have 3p, the first set, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, and then you go down over here. This here is 4s. This is level 1, 2, 3, 4, 4s, 2, And then you have 3d10. So because D has 5 orbitals, the first one, the second one, third one, fourth one, and fifth one. And that's why there's 10d orbitals. 10d orbital electrons fit in 5 separate orbitals. Okay. And then after 3d here, we go to 4p, 4p1, 4p2, 4p3, 4p4, 4p5, 4p6. And then you just keep going. So let's go ahead and talk about hydrogen atom. So hydrogen atom, the electron configuration is 1s1. That's only one electron in there. Okay, so when I draw the 1s electron, let's say this is the orbital box. I want to fill in 1 electron and 1s. We'll start with spin up first. Okay, so spin up electron, this sole electron in hydrogen atom, we can describe it using quantum numbers. So the quantum number description will be level 1, L0 because it's s orbital, and then ML is 0 because 0 and 0 is the only option. And then MS would be spin up. Ta-da! Okay, the first electron in the hydrogen atom. Now we go, okay, well, let's add on. We want to write it for this electron in helium. So in helium, you have 2 electrons. It's 1s2 because there's 2 electrons in there. So if you were to fill it, 1s orbital here, you go spin up and then spin down. Okay, so there's 2 electrons in here. That first electron is described using these series here, the same one. The second electron so the second and the final electron in helium, right there, we can describe it as N is 1, L is 0, ML is 0, because it's the same orbital. And then MS, in this case, will be -half. So helium has 2 electrons. The first electron is described using these 4 numbers, and the second electron is described using the second series, 1, 0, 0, -half. So because it does repeat, like every atom after that contains an electron, like say, for example, we did lithium atom. Okay, in lithium, you have 3 electrons and 3 protons because the number is 3 right here. Okay, so when we have that, it's 1s2 and then 2s1. Agree? So I could, literally for electron configuration, you would draw. So here's a box for 1s, and then here's another box for 2s. And then you will say, well, you fill the lowest level first. So it's spin up, spin down, and then spin up. Okay, now the first electron was the same as this guy here. So I can go ahead and write now. So this electron here, when we want to describe it, as N equals to 1, L equals to 0, ML is also 0, MS is spin up. And then this electron, the second electron, was N equals to 1, L equals to 0, ML equals to 0, and then MS was spin down. Okay, now obviously these two are the same. So when they describe it, they always go to what is the last electron in there, because everybody else was copied from the atoms before that. Okay, so the last electron in lithium is unique to lithium. So that guy here, lithium's last electron, let's go ahead and describe it. It's N equals to what? 2, and then L equals to 0, because it's 2s orbital and it's the first and only one, so ML is 0. And then they spin up, so MS will be +half. Okay, so that's how you would do it. Now, these are the simple ones. So let's go ahead and give you a problem that you might see for, like, a question that you would see like in class or on a test. So it says here, what quantum numbers do we use to describe the last electron of chlorine atom? Okay, the last electron in chlorine. So then we better go and look at our periodic table, okay? The periodic table says chlorine is right here, number 17. So there's 17 electrons. So we got to split all 17 up. So what are the electrons in Cl? So it's from the periodic table, 1s, 2, and then 2s, 2, and then 2p, 6. All of those are in the Cl. And then on top of that, you have 3s, 2, and then you have 3p up to this number. So 3p, 1, 2, 3, 4, 5. Okay, so that's all the electrons that are in chlorine. So there's 17 electrons, remember? So in chlorine, there's 17 electrons in there, and it goes in, the first one goes in 1s. There's 2 of them right there. And then we go to 2s, there's another 2. And then we go to 2p, there's 6 there. So far you've used up 10 electrons, right? So now we got 7 more we gotta fill in. And then you go, the next one is 3s. There's 2 more, that's 12. And then 3p, 5. That's how you get all 17 electrons. So while we're at here, I'm talking about electrons here, let's talk about valence electrons versus core electrons, okay? So core electrons are the ones on the inside level. So level 1 and 2 are inside, level 3 is the outside, agree? So these guys here are how many valence electrons it has. So on the outside layer, okay? On the inside layer, these are called core electrons. Okay, so the reason why we want to distinguish them is because if you notice, our groups are arranged on the periodic table according to how many valence electrons. Valence electrons are important because they're on the outside and they are the reason why things react. The ones on the inside are core electrons. They are so buried deep inside there that they're not really reactive. They're not really taking part in the reactions. The valence electrons are all taking part in it. So group 7 has 7 valence electrons, and the 7 are from 3s2 and 3p5 for chlorine. Okay, now if you had a transition metal like say titanium, you will actually count the level 4s2 here, and for titanium there's 2 more in D. You also count the D orbitals. So I'll write it out here. So if, on a side note, transition metal include the outside layer plus the D orbital right before it. So that means like for titanium, I'll give you an example. Titanium is pretty long. So titanium has 22 electrons, right? So is everybody in there? I'll write it out. All 22. So we'll go ahead and do 1s2, 2s2, 2p6, and then 3s2, 3p6, 4s2, and then 4p, not 4p, 3d. Whoa. 3d2. Okay, so that's what we saw here. Up to this, and you have 22 electrons right there. So this here, the 4 is the outside layer, right? And then we say the D that's right next to it, right before it. Well, technically, because 3D, D is before, but we write the D as the outside because of the energy level mixing. So I wanted to show you a picture of that right here. So with every increasing electron level, 1s and then 2s and then 2p is a little higher, 3s is higher than 2s, 3p is a little higher than 3s. Now, once you get to level 4, 4s is right there high, and then 4p is there, and then 4d is higher, right? You start seeing that level 3d was actually higher than 4s. So I like to write my configuration where I just go ahead by filling my order from the lowest to the highest. So I will write 4s after 3p. So 3p and then 4s and then 3d. Okay, the reason why I write that, but the D here and the S for this guy is both counted. So even though I say right before it, I do write the orbital right after, so you can kind of see these are the outside. Okay, so this one here, all four of this will include the transition metals. So these are the valence electrons for transition metal. Okay, they include 4s2 and 3d2. There is argument and debate. Sometimes they don't want to count the D, sometimes they count the D, but we'll go ahead and count it. Okay, so that's the valence for transition metals. And then this is the valence for the regular main table. You don't have to worry about a D, just the outsidemost layer. If you had transition metals, you count the outside plus whatever right before it. Okay, so now, since it does get long at some point, there is a shortcut way to write electron configurations. The shortcut way is to clump everybody in the inside layers, the core electrons, as one of these noble gases. Okay, so we were talking chlorine, the noble gas right before that is neon. So neon has all of these guys. So neon has 10, is 1s2, 2s2, and 2p6. So instead of writing that, I sometimes can write the short form and say this is neon, and then 3s2, 3p5. So that's acceptable. That's a short form of it. Okay, for titanium, for example, if we wanted to write it, we would say who's right before titanium? That would be argon, right? So argon is number 18, titanium is 22. So you literally write argon, and then you put, well, I got two more, 4s2, 3d2. Okay, so that's how we would be writing our shortcut, the short form of electron configuration. So anyway, we were talking about electron configurations. Now let's go back to the question. It says it was the last electron for a chlorine atom, and you want to describe is this guy, the fifth guy. Okay, so I'm going to focus in on that fifth electron on chlorine. So let's go back over here, and I'm going to draw out this valence level here. So basically, I'm going to just write boxes for each one. So it's 3s, and then I have 3p. Okay, now on the 3p, there's 3 boxes, right? So hopefully that's enough space for 3. There you go, right there. Okay, so we have 3s and 3p. So you have to fill up s first because s is lower energy than 3p. And then we want to go ahead and fill up fill up the electrons and stop at the fifth one. Okay, so when you have this and degenerate, so degenerate means same energy level like 3p, x, y, and z. They're all the same energy level. So you go spin up, spin up, spin up, that's 3, and then spin down, spin down. So this guy here, that is the last electron that we want. Okay, so what's the quantum number that describes this? So this is level 3p. The first one is x, y, and z, right? So this is the first so this one here, this guy, because there's 3 of them, remember the ML is -1, 0, and +1. Okay, so this guy, the ML will be 0. And then so if it's level 3, N equals to 3, L equals to 1, because it's p orbital. Because L equals to 0 means it is s orbital. So this was L0. This one, L is 1 because it's p orbital. Okay, so we're focusing on p orbital because they want you to write the electrons, the last electrons quantum number. So this is the last one. So level 3p, and which one is it? The one in the middle. So it's 0. This is -1, 0, and then +1. So that's the 0 one for the ML here. And then for the MS, is it spin up or spin down? It's spin down, so it's -½ So those are the 4 numbers you can use to describe that electron, the final electron that goes into chlorine atom. Okay? We can go ahead and do it for this guy, titanium. We just did it earlier, right? So we want to go ahead and describe the last electron for this guy. So we'll show an example. Titanium was 4s2. And then we had 3d5. So that's going to be bigger. Well, I hope there's enough space. Woo-hoo. 1, 2, 3, 4. Okay, just enough. So there's 3D here, okay? So remember, this one is -2, -1 for the ml. -2, -1, 0, +1, +2. Okay, so we are trying to describe this guy, the last one. So 4s, we fill up, spin down, and then 3D, we spin up and spin up. Okay, so that last electron for titanium here, that guy, we're going to describe it as n equals to what? Level 3. Okay, what's the L? L0 means s orbital, L1 means p orbital, L2 means d orbital. So this is L2. Okay, and then we're at ml, the second one. So that would be -1. And then what's your ms? Is it spin up or spin down? So this is spin up, so we'll go +half. So that's how we would describe the electrons using quantum numbers. I think this is cool. All right, so we are okay with doing atoms. Let's try doing ions, okay? So let's try a cation. So we want to describe the quantum number for this cation here, Al3+, okay? So describe, so quantum numbers for last electron in Al3+. Okay, so then we got to decide what Al3+ configuration is. So Al3+ is aluminum, is 13. 3+ means it lost 3 electrons. Take out 1, take out 2, take out 3. Who does it look like? Aluminum 3+ looks exactly like neon. Okay, and that's why we say the peer pressure, everybody wants to be like the noble gases. So it looks exactly like neon. So the electron configuration is just whatever neon's configuration is, which is 1s2, 2s2, 2p6. Okay, so remember, these are the valence electron. This one here is in the core. The valence is the outside layer. So to describe the last electron in 2p6, I'm going to go ahead and write it out. So we have level 2s, and then we have level 2p6, well, 2p and then 6 electrons, the last one. So it's spin up, spin down, spin up, spin up, spin up, spin down, spin down, spin down. Notice how you go up, 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 and then down, down, down. So that guy here is the last electron. We want to describe that guy. So this is level 2p, right? So n equals to 2. And then L equals what? Because this is 0, this is 1. And then ML means, which one is it? It's -1, 0, or +1. It's the one in the third one, so it's +1. And then we want to go with the MS, spin down, so it's -1/2. Okay, so that's how you would do and a cation. Let's try an anion here, okay? So the anion we want to go ahead and try is, okay, I'm running out of space. So here's that one, here's that one, and here's that one, and that one. I'm just separating them. So we have one more right here. Okay, so we're gonna do I negative. Okay, so what does iodide look like? Iodide is right here. Woohoo, this guy has a lot of them, right? So this one, if you want to write everybody, it'll take forever. So what I like to do is say everybody in krypton plus whatever's on the outside. Okay, so let's go ahead and see what everybody in krypton looks like. So everybody in krypton. And then after krypton, we have 36 is krypton right here, okay? So we have level 1, 2, 3, 4, 5. So 5s2, and then 4d10, okay? and then 5p, 1, 2, 3, 4, 5, and then it's -1 charge, so it's 5p6. So everybody likes xenon. Actually, I lied, so I shouldn't have written that. It's actually exactly like xenon. Because it's an ion. If it was an atom, we would have said everybody in krypton plus all those guys. Okay, so I'm going to go ahead and list out everybody in here in xenon. So iodide has the same ion configuration as xenon atom because it gained 1 electron. So it's 1s2, 2s2, 2p6, 3s2, 3p6. And then if you ever like forget, you always just look in your periodic table. So this is like 3p6. And then you go down, this is 4s2, 3d10, and 4p6. And then you go down, this is 5s2, 4d10, and this is 5p6 right here. If it was an atom, I atom would be 5p5 right here. This is 5p6, okay? So I'm gonna go ahead and continue writing until I hit 5p6. So 3p, and then we have 4s2, and then 3d10, and then after 3d, we go back to p, 4p, 6, and then 5s2. Ooh, running out of space. Continue down here. 4d10, and then 5p6. Okay, so that's how all the electrons in there. Now, if it was an atom, it would have stopped at krypton, which is, krypton is all of these guys in here, from here to here. And then plus these guys and 5p5, okay? But this is an anion, so it's exactly like xenon. So the last electron is on here. So I'm gonna go ahead and just draw the 5p side, okay? So we are level 5p, and 5p we have 3 of them. So it's 5p6, 1, spin up, spin up, spin up, spin down, spin down, spin down. So that guy, the last electron in there, we want to describe him. It's going to be n equals to level 5. L is 1 because it's p. And then ml is the last one. So it's -1, 0, +1. So it's +1. And then ms will be spin down. So it's -12. Okay, so that's how we would do an ion. So while we're at all these configurations, we're talking about valence and core. Now remember, we want to talk about, this is iodide. The valence for this guy is the outermost because he's not a transition metal. So it'll be level 5 is going to be iodide. It has 8 electrons because it looks like exactly like xenon. Okay, so let's go and talk about ground state versus excited state. So configurations for electrons are by default always ground state, unless they mention it's not ground state and it's excited. So what is the difference between ground state and excited state configuration? Okay, so ground state, electron configuration. Okay, is the most stable state, like what we always talk about, like you fill it in order from the lowest energy to the highest energy. Now, excited state is basically one electron, one or more is pumped, got excited, they absorbed a photon and it jumped up a level where it doesn't belong. Typically, it jumps up to the outside, empty levels. Okay, but you can see one electron out of place. That's excited state. So excited state, electron. So that means there's a lot of options when you're excited. I mean, you know which photon is going to hit and how much energy and which one will take it. So there's a lot of options. So a lot of times they'll say, which one of these look like an excited state configuration? That means one of them, at least one of them will be out of place. Okay, so example is we want to go ahead and do Al atom. And then we'll do Al star atom. Star means excited, okay? So aluminum would be, looking on a periodic table in case we don't remember, is right here, number 13. So it's 1s, okay, 1s2, 2s2, 2p6, 3s2, and then 3p1. So I'm right there. So it would look like this. 1s2, 2s2, 2p6, 3s2, 3p1. Now, if I wanted to do a short form, neon will be the guy before it, and this here, you could write it as neon instead if you really wanted to. Okay, so when an example of an excited atom, one of these atoms got shot up, usually it's not going to touch the core because the core is so hidden and secure and safe. It's going to be one of these valence one that will take a hit if it's lower energy excitation. Okay, so for example, one of the possible forms of excited is 1s2, 2s2. I'm going to keep the core the same. I'll just move one of the 3s orbitals. 2p6 and then 3s. You see one of them popped up and went to level 2, 3p2. See how like one of these guys went up in this on one level where it's supposed to be ground state like this, excited state, one of them is popped out of place. So that's how you can tell it's excited versus ground state. Okay, the star means excited. After absorption of a photon. All right, so we got that. Now, sometimes you will see exceptions. With everything we have, we always show you exceptions. So an exception is when you sometimes fill d orbitals by 5, for example, 3d5 or 3d10. 3d10 is the most stable option. So completely full, so full orbitals are most stable. So they prefer to fill up all the orbitals, or half orbital is pretty stable. So if you can't get full orbital, they'll try it for half. Okay, so I'll show you when that can change. So let's take a look at chromium. Okay, so we want to take a look at chromium, and then we want to take a look at copper. So these ground states here are not what you would expect it to be. Okay, so ground state, ground state. So let's take a look at chromium first. Chromium is right here, the fourth guy in your 3D. So basically is blah, 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 blah. Okay, I'll read it out. I don't blah, blah, blah for you. Okay, I'll be patient. 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, and then 3d4. Okay, so you're at 3d4. I'm going to go ahead and write it out. So what you would expect is from the table is 4s2 and 3d4. What they observe is actually 4s1 and 3d5. So if you were just blindly looking on a periodic table based on the trends we see, we would say, well, 1, 2, 3, 4, 3d4. Now, because it's so close to 3d5, it's going to steal that 1 from 4s to fill at 3d because it actually prefers, even though it's kind of excited, it's not really excited. This is a ground state. It looks like an excited. It's because this configuration 3d5 is more stable than 3d4. It's more stable than like this. AR 4s2 3d4 because there's 4 in there. So they prefer this. So this here is the ground state. So that's when you have an exception, when you can form 5 and you can form 10. Okay, so this is like double check. This is single check. You like it. So that's my preference. Okay, so let's take a look at copper. Now, if you looked at copper, copper was the 9th guy in there before zinc. Zinc is the 10th electron in orbital. So it's 3d9. It's 4s2, 3d9. But what you observe is they steal that 1 electron from 4s, they fill it up to 3d10 because it's more stable. So what you will have is say AR 4s1, 3d10, because they prefer that it's more stable. That's their ground state. So these are the exceptions that you see. And on your slides there, you'll see more exceptions, but it's usually because it's completely filled or half filled of orbitals. It applies to d orbitals, and sometimes you see on p orbitals as well. But these things you usually observe more in transition metals. Okay, so I can write down the other option you would have seen is more stable than Ar4s2 3d9. Because it's so close to that stability for that 3d10 right there. Okay, so let's do this. Okay, now we want to go ahead and do more electron configuration. Now I want to show you how to look at paired versus unpaired electrons. Okay, so I guess we'll go ahead and define it, what paired and unpaired electron means. So diamagnetic is anything that has no unpaired electrons. Okay, and then paramagnetic is anything that has one or more unpaired electrons. So when it comes to being able to see if it's para or diamagnetic, it's because we can use it to see if you can magnetize certain things or not. Trying to show you some pictures. See if there's pictures here. Right here. So on your magnetic properties, right here. This is going to be slide number 50. Okay. It says here, paramagnetic stuff will be attracted to a magnetic field, and stuff that's not magnetic is not attracted, it was slightly repelled by magnetic field, but it's diamagnetic, will have no magnetic field. Okay, so if it's unpaired, you can basically like magnetize it. So let's take a look at one example. It says here, draw out S electron configuration. So it's for sulfur, okay? Determine number of unpaired electrons. So a lot of times when we want to look at paramagnetic, people always think, oh, well, if it's even numbers, it's going to be paired. If it's uneven, like odd numbers, it will be unpaired, right? Actually, that's not true, because remember, we're doing spin up, 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 down, down, down. So that doesn't always stay true. So let's take a look at this, okay? So sulfur, if you look on the periodic table, is number 16, right there. So it's 1s2, 2s2, let's see, yeah. And then 2p6, and then 3s2, 3p4. Okay, so we're 3p4. Okay, once we have that, you're like, oh, 3p4. So everybody in here is paired. We don't have to worry about that. We want to look at unpaired, so we draw the last one, okay? If I drew all of it, it will take me forever, and my art isn't that good. So spin up, spin up, spin up, spin down. You're like, huh. So if you thought even numbers means all paired, that's actually wrong, because this is an even number and you still have unpaired electrons. Okay, so you gotta make sure you don't fall for that. Always draw it out just in case to see what it looks like, and it doesn't take that much time. Okay, so this one here is paramagnetic. So it'll be attracted to a magnetic field. Okay. Okay, so this one here, we have how many unpaired electrons? We have 2 unpaired electrons. 2 unpaired electrons. Okay, and that's level 3p. Okay, so that's how you can tell stuff that's magnetic or not. So let's do some more examples, okay? We want to tell if it's paramagnetic or diamagnetic. Let's do ruthenium. So ruthenium is right here. It's the 6th one on the group. So it's 1, 2, 3, 4, 5, 6. Okay, so this is level 4D6. Okay, so it's level 4D because this is 1, 2, 3, 4, 5s, and then 4D6. Okay, so I can basically say ruthenium is everybody in krypton, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6. Everybody in krypton, okay? So I'm gonna go ahead and write that out because I'm getting tired of writing all the long list. So everybody in krypton, and then 5s2, 4d6, okay? So these guys here are my valence electron, because we want to count them. So for ruthenium, and if I want to draw it out, I'll draw the valence electron. You'll have level 5s, and then we have level 4d. Okay, 4d has 1, 2, 3, 4, 5 of them. So it's 4d, 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 4d. Okay, so we want to do spin up, spin down. We fill that one first. Spin up, 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 up. So that's 5, and then down. Okay, so we have this one here. How many unpaired? We have 4 unpaired, and this guy is paramagnetic. Okay, so let's go to the next one. We want to do selenium. Okay, selenium is Se. It is number 34 right there. And everybody in argon plus some stuff. Okay, so everybody in argon plus 4s2, 3d10, 4p, 1, 2, 3, 4. Okay, so it's 4p4. 4p4 right there. So go ahead and write it out. Is everybody in argon plus 4s2, 3d10, 4p4. So these two are the most outside layer because it's the main table is not transition metal. These two are my valence electrons. Okay, so when we draw the valence, we can do 4s, and then we want to do 4p. We go 4s2, up, down, 4p4, 1, 2, 3, 4. So this here is also paramagnetic. So don't think if it's even numbers, it's going to be all paired, because that's not true because of the spin up and spin down thing that we're drawing. Okay, so that one's paramagnetic. Let's try with some ions this time. Let's look at Al3+, and then we want to do S2-, and then we want to do Fe3+. Okay, so let's see if their para are diamagnetic here. That's 3 here. So aluminum 3+. Aluminum 3+ is right here. Lose 3, 1, 2, 3. It looks exactly like neon. Okay, so when it looks exactly like neon, it's 1s2, 2s2, 2p6. Everybody's filled. That's completely filled, right? So I can draw it out. I guess I'll draw the 2s right here. Everybody's filled. So this is diamagnetic. Okay, now not all ions are always diamagnetic. I'll show you some of them are not. So let's do S2-. S2 negative is add 2 electrons. So it looks exactly like argon. So argon here is 1s2, 2s2, 2p6, and then 3s2, 3p6. Okay, well, that one's everybody felt too. So, okay, let's do that. It's level 3s, and then level 3p. Spin up, down, spin up, 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 down, down, down. Okay, so this one's all, this is also diamagnetic. So far you're like, yeah, everybody's diamagnetic. But what about this guy? This one's not diamagnetic. I want to show you why, because iron is right here. It's number 6 in 3D. So 1, 2, 3, 4, 5, 6. Okay, so this is 4s2, 3d6. So that's iron for atom. Then you got to remove 3 of them. So for iron atom, I can show you is basically everybody in argon. And then we have 4s2, 3d6. Okay, so we have to remove 3 electrons, agree? When you remove 3 electrons, they're gonna go ahead and take out 1 from the D, so you have 3d5, and you're like, but I need 2 more. Can I take 2 more from 3? Yeah, you can, but then there's 2 right there they can take, so they can keep the 3d5. So what they end up doing is like this. To get Fe3 plus, you actually have argon, and then you have 4s, but it's 0 here, and then you have 3d5. That's what it's going to look like. It's crazy, but it's because 3d5 is preferred here. Okay, so now you have nothing in here, 4s. This is still the ground state because this is more stable than the other option, what we would expect it to say, take it all straight from the 3D. Okay, so that one's empty, and then you have 5 of them. 1, 2, 3, 4, 5. Okay, spin up, 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 up. You're like, oh, all of them are unpaired now. Okay, so this one here is para. Okay, might as well, while we have this drawn out, let's go ahead and draw it out. So this one is 4s, spin up, spin down, and then 3d6. So spin up, 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 5, 6. Woohoo! Messed up that one. So this is 3D. So this is also paramagnetic. Okay, so we got those down. So that is a lot of the stuff I want to talk about electron configurations. Time to show you some pictures. Let's see what pictures we want to show you. Yeah, I already showed you this. This is slide number 17, the levels of it. That's a cool picture to look at because of how the levels are mixing. Okay, so these are degenerate, and every time you go higher, you see how when you get the 5s, it's mixing with 4d. So that's why when we draw a periodic table, this is 4s and that's 3d, and this is 5s, this is 4d. And when it's F right here, it actually goes down 2 levels. It's weird, but that's because it keeps mixing. Okay, and then on the next slide here, slide number 18, here's another cool one. It says, so you fill from the lowest energy to the highest energy. This is called alpha principle. And then same sublevel, like 3Ps all have the same energy. That's why we were writing like these guys all the same level. And then 3D all the same level. But then from 4s to 3D, there's different energies. Okay, and it says no more than 2 electrons per orbital. So that's Pauli exclusion principle. And Hund's rule tells you go place electrons that are the same energy. So degenerate ones, you spin up, 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 and then before you come down, down, down. Okay, that's Hund's rules right there. So that was that. We talked about it. And then we talked about valence electrons and core electrons. So there's lots of pictures on your periodic table telling you all these things. And all this is on your slides. Okay, so we were talking about irregular transition electron configurations. So over here, I showed you chromium and copper, we have molybdenum and palladium. They're also weird. So if you look at the periodic table, you would expect molybdenum to be the fourth one right here. 1, 2, 3, 4. Instead of the 4, they stole one from the S and they have 4d5. Same thing for palladium here. Instead of 8, they steal 2 and they get 4d10. That's because it's more stable. So these are just some ground state that are not what you expected it to be, but it's more stable that way. Okay. So that was slide number 32. We are moving along. And then our predictable charges, we already talked about it. So let's go ahead and talk about periodic trends now. So when we're talking periodic trends, I actually made slides to summarize it, but I think it didn't come up. Well, you can still see it. So it means small. I don't know why the LL came on the bottom, but whatever. So we're going to rank a few things. We're talking about size and metallic character. So size is, if you go down, it's going to get bigger. So you have small to big. And then when you go to the right across the periodic table, it gets from big to small. And I'll explain why all this happens. And we'll also talk about different kinds of size comparisons. Metallic character is like, which side of periodic table is more metallic? Oh, well, the side that has more metals is metallic side. So from here to here is more metallic. And then going right across the periodic table, it's going to be less metallic. Okay. But when you go down, the bigger it is, the more metallic it will be. And then I'll explain why that is the case. So that's that one. And then we have more trends here that we want to talk about. It's called ionization energy trend, electron affinity. There's no real good trend. So instead of electron affinity, I'm going to go ahead and introduce you electronegativity that actually belongs in the next chapter. But we'll go ahead and do it now. So this is what chapter 9. Electronegativity is really focused on in chapter 10, but I'm going to go ahead and introduce you electronegativity here. Okay, so electronegativity, ionization energy, the trend is the more electronegative side is to the top right corner. Okay, and then ionization energy gets bigger as you go to that side as well. So these are the trends that are the opposite of the other one, two sides. So I separate them by two kinds of categories. So let's take a look at sizes, okay? So the first thing is sizes. If you take a look at this picture here, if it goes down, the radius of your atom gets bigger and bigger. Why? Well, because my orbitals are getting bigger and bigger. Level 1, 2, 3, 4, 5, it's getting bigger and bigger. Why? Yeah. So obviously it's going to get a bigger size, okay, as you go down group. Now, if you go to the right here, it's actually getting smaller. Why is that so? I have to explain that to you. Okay, now, I guess you could just memorize it and not know why, but I like to know why so I can remember things without memorizing it. So let's talk about the sizes right here. Now, after we talk about these sizes for the atoms, I want to show you sizes for ions as well, okay? So let's do this. First trend we want to talk about is sizes. So sizes. Size of atom gets bigger as we go down a group on the periodic table. Why? Because N level are higher. So orbitals are bigger. Okay, so going down a group, it gets bigger. Okay, and then we want to go, this is part 1, so part 2, we want to go across. So size gets smaller from left to right. if you're on the same row, okay? If you're on the same period, we're not talking different periods here because different periods obviously smaller, bigger. But if you're all going just one straight from left to right, it is going to get smaller. So I have to explain why it gets smaller, okay? So the reason it's smaller is because effective nuclear charge. We call it Z effective. Okay, I started writing ZEFF because I got lazy like this. And then my students started coining a new term, they call it ZEF, because ZEF gets bigger. So anyway, you can call it ZEF, but nobody will know what you're talking about except our class. Okay, so because Z effective is increasing, or ZEF. Okay, so let's draw out what in the world is effective nuclear charge. Okay, so when we were talking in early chapters there, we had Z as number of protons, remember? Z is atomic number, which is the number of protons. And then we have A, which is mass number, which was number of protons plus neutrons. Okay, so that's what we learned a way long time ago. So this has to do with that. It's basically the number of protons, but then it has to do with like your core electrons versus your valence electrons. So I gotta draw it out, okay? So let me draw out a series here. We wanna do lithium, and then we wanna do beryllium, and then we wanna do boron, and then keep going, carbon, nitrogen, oxygen. I'm not really gonna draw all these. We'll draw like the first three and you can see the pattern, okay? And I'm pretty sure the textbook or the slides actually has pictures of it, so I can just show you that. Their drawing is a lot nicer than mine, but for us to understand it, it's a lot easier if we actually did it and drew it out. Okay. So lithium on the periodic table is number 3, has 3 protons and 3 electrons. Beryllium is next, 4 protons, 4 electrons, 5, 6, 7, 8. And kind of go, like you can keep going, but I'm just gonna do like the first 3, okay? So we'll draw these, maybe we'll do a 4th one if we feel like it. So 3 protons, therefore I have 3 electrons. Okay, 4 protons, I have 4 electrons. I have 5 protons, 5 electrons. Okay, we'll do one more. 6 protons, 6 electrons. Okay, so I want to draw the picture. Now, before I do that, I need to know in my electron, what's my electron configuration is 1s2, 2s1. This one is 1s2, 2s2. This one is 1s2, 2s2, 2p1. This one is 1s2, 2s2, 2p2. Okay, so the outside layers are my valence. Okay, I underline the valence. So valence, 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 valence. So the ones on the outside are valence electrons, and the one inside the level 1s is my core electrons, okay? So I guess I'll write down core. Okay, once we have that, let's draw a picture out. No, Z is really just number of protons, but Z effective has to take it out into number of protons and then our electron configuration arrangement. So if I were to draw a really simple thing, let me draw the protons in the nucleus, okay? So there's 3 protons, so I put 3 protons with positive charges here. And then I have the core electrons and have the valence electrons. Obviously, I'm drawing a really simplified version, okay? Because I'm not talented enough to draw all these other orbitals. So we're just like a rough diagram. So this is my core level. This is my valence on the outside. Okay, So how many electrons in my core? I have 2. So I'll draw 2 floating electrons. Here's an electron, here's another electron. My valence, how many electrons do I have? I have 1, so I'll just draw 1 in the valence level. Okay, so what happens is Z effective says that these 2 in the core are mixing. So the protons in there are being shielded by the core electrons here. So the Z effective is basically the force that it's feeling, the pull from the inside, from the nucleus to the outside most layers. Okay, it's actually kind of covered up by the core. So it's 3 positive charges, but then you add 2 electrons, which is negative charges. So you subtract 2, so your Z effective is only +1. Okay, so that's my Z effective for the first guy. And then if you look at the next picture here, the Z effective is increasing because now your core is 4 and you have 2 electrons, and then you have 2 electrons flying on the outside. The ones on the outside, it really doesn't, they're not being shielded, right? So you want to say, what's my Z effective here? So it will be 4 minus 2 electrons, which would be +2. So this one, Z effective is +2. So basically overall, this valence electron is feeling a pull of +1. These 2 valence electrons are feeling a pull of +2. Something that's feeling a stronger pull of +2 will be smaller than something that's pulling a pull of just +1. So for boron, let's take a look at what the pull is, okay? So it's 5+ in the middle, and then you got 2 in the core, and then we got 3 in the valence. So the ones in the valence, what pull are they feeling? It's Z effective of 5, and then -2, you get +3. So you see how the Z effective is getting bigger as you go this way? So because Z effective is increasing, okay? The pull from nucleus to valence is stronger. It can hold the electrons tighter and closer to the nucleus. So that's why the size gets smaller, because it's pulling it closer together, okay? Obviously, I'm not drawing to scale because you saw this was big and this small, and I somehow drew this one bigger, but it's getting smaller as you go, okay, I promise. And then this one here, you got 6 in the middle, and then you got 2 on the core, and then you got 4 in the valence. So the Z effective for this guy is going to be 6 minus 2, which is +4. Okay, so that's why you can explain why sizes are getting smaller as you go to the right across the periodic table, is because Z effective is increasing. Okay, so going down a group gets bigger, going to the right gets smaller because Z effective is increasing. Okay, so question time, okay? Which one is bigger? A, N, or F? B, C, or G? C, N, or AL? D, AL, or G? Okay, let's take a look. N or F? Which one's bigger? N or F? Going to the right gets smaller, N will be bigger. Okay? And then C or GE? C or GE? Going down a group, GE will be bigger. All right, N or AL? This is smaller this way and smaller to the up, so AL is bigger, okay? And then AL or GE? This one here is hard to compare because going down is bigger, but going to the right is smaller. So I'm not going to ask you guys questions like this. So this is, can't be determined from trends. You can, however, look it up and see exactly what the size is. Then you can tell who's bigger, right? Let's see if we have a picture of that. Let's see if we can find if there's a picture of the sizes. Aluminum. I might have it. Aluminum, germanium. No, not on my list. Sorry, guys. So we won't be able to tell that part. But if you look on a textbook, I think we have the list right there. But I do have a picture that we can kind of see. So aluminum, germanium is right here between Na and Ar and Kn. So you see how this trend here on slide number 43, it shows you the radius goes down a group, gets bigger, goes down a group, gets bigger, but then as you go across, it gets smaller, right? So we were talking about aluminum and germanium. Aluminum is number 3 from Na, is Na, and then magnesium and aluminum. So this is aluminum right here. And then where's germanium? Germanium is potassium, and then plus the zinc. So that's zinc right here. So this is 1, 2. Germanium is right here. So you can kind of see, okay, based on this chart, I can see that aluminum was bigger, okay? But you actually had to look at the actual numbers because the radius for the aluminum was bigger. But you were opposing trends over there, so you couldn't quite tell just from a trend. Okay, so there is this right here, you could tell, but I'm not gonna like ask you based on trends. Okay, so that's that. So it's kind of cool, you can see the trends on the picture right here. All of them are recorded, basically. Okay, let's keep going. We want to talk about sizes of ions now, okay? So let's talk about ions. So when we talk about ions, let's compare an atom to a cation, an atom to an anion, okay? So aluminum atom versus aluminum 3+, okay? Aluminum atom is neon plus 3s1 and 3p, not 3s1, I like. It's not 3s1, it's 3s2. 3s2, 3p1, and then aluminum 3+, you lose these 3 here, so you just have neon. Okay, so can you say who's smaller now? Literally, this guy had extra stuff on the outside. Aluminum 3+ doesn't have the extra stuff. So cations are smaller. In general, cations are always smaller, okay? Smaller than the atom it came from. Okay, let's talk about anion then. Anion, we want to do chlorine versus Cl negative iodide, chloride, okay? I don't know why I said iodide. Okay, it's getting late. So chlorine is right here. Okay, so it's next to argon. If you take one, it looks just like argon, okay? So I'm gonna go ahead and write down chlorine, the atom is everybody in neon. There's aluminum, and then we have chlorine here. So after neon, you got all this stuff, and you have 3p5, okay? So 3s2, 3p5. And then Cl negative would be basically all of that plus another one. So it'll be, technically it's everything that looks like argon, or we can say it's, if you wanted to compare, it's 3s2, 3p6. Okay, so you have an extra right there. And plus, this extra electron is increasing electron repulsion. Okay, so it makes it bigger because there's an extra electron right there. Okay, so anions are bigger than the atom it came from. Okay, because it has to do with the extra electrons that you put in. You have extra electron repulsion, which spaces things out further. So like it makes it bigger, basically. It's repulsing, gets to be a bigger space. Okay, so that's that. So if I asked you, which one is bigger? So there's the big question. Which is bigger? A, you have S or S2 negative. B, Ca or Ca2 plus. So then you'd be like, well, obviously the bigger one is the anion, and obviously the bigger one is the atom right here compared to the cation, just because of the trends that we just told you about over here. So those are ions and the atoms it came from, okay? So there's another series of ions I want you to consider. So they are called isoelectronic species, okay? So let's go to the next page because I'm running out of space here and I want to draw it out again. I'm drawing it out because I want to explain it, but once you understand it, you're not going to have to draw it out. But it's cool to have an illustration, okay? So we want to talk about isoelectronic species. What do they mean? They have the same electron configuration. Okay, everybody has the same electron configuration. So I'll give you an example of isoelectronic species here. I have O2 negative, F negative, and then I have neon, and then I have sodium plus and magnesium 2 plus. Okay, so the reason why these are isoelectronic is, take a look over here. So neon is right here. Okay, number 10. So I'll push this up a little bit. Oh, now you can't see. Right there. Okay. So neon is 10. O2 is O2, O8 plus 2, so it's 10. F is plus 1 electron, so it's 10. Neon is 10. And then sodium is right after it. Sodium lost 1, so it's 10. And magnesium lost 2, so it's 10. Everybody has the same electron configuration as neon. Agree? So that's one set of isoelectronic species. Another set is, it will be S2 negative, or you can even do P3 negative, but that's not common at all, it's rare. So we see S2 negative, Cl negative, Ar, and then we have K plus and then Ca2 plus. That's another isoelectronic series, okay, species here. So anyway, give you one example here, and then we want to say, when you have isoelectronic species, the more negative the ion, the bigger the size, okay? And the more positive the ion, the smaller the size. So basically, it goes from big to small, okay? It goes from big to small, so big to small. Why? Because Z effective is increasing. So I'm going to go ahead and show you the Z effective calculations here, okay? So O is Z original is number of protons is 8, okay, 8 protons. And then we have 10 electrons, because it looks like neon, and everybody has the same configuration, and 1s2, 2s2, 2p6. Everybody looks the same. So that's one. This one, Z here is 9. Z here is 10. Z of 11. Z of 12. Okay, everybody is isoelectronic, right? Everybody has 10 electrons. Everybody is 1s2, 2s2, 2p6, 1s2, 2s2, 2p6. Whew. Don't know why I wrote that one on the bottom. Okay, let's erase that. Right there. Okay, so my valence are 8 electrons. My core are 2 electrons. And I have to subtract out the core electrons, remember, to find my Z effective. So my Z effective is 8 protons minus 2 in the core. I have plus 6. This Z effective for fluoride is 9 minus 2, I have plus 7. And then the next one is 10 minus 2, I have plus 8. And then Z effective of 11 minus 2 is plus 9. Z effective of 12 minus 2 is plus 10. So the bigger the Z effective, the smaller the size will be, because it's pulling you closer to the nucleus, to the center of the atom, or the ion in this case. Ions or atom, whatever the isoelectronic species is, closer to the middle. So it's bigger because smaller Z effective, smaller because bigger Z effective here. So isoelectronic species have the same electron configurations. The more negative it is, the bigger the size will be. Okay, so that's how you explain that. Now, here's a question now. So which is bigger? BR negative or KR? And then you're gonna look, okay, BR negative or KR, how am I going to tell? Look, isoelectronic, BR negative, KR, same electrons. The more negative, the bigger. Remember, so this is negative charge, BR negative. So BR negative will be bigger. Okay, now if we give you a whole list, BR negative, KR, and then RB plus, let's arrange it, okay? So we want to arrange for the next series here, the size will be S, 2 negative is the biggest, and then actually not SE, it's S. It's not S, it's SE. It's weird software. Up here. Okay, we have SE, and then we have BR, and then we have KR, and then we have rubidium, and then we have strontium. That's how you arrange the isoelectronic. So another isoelectronic series would be S2 negative, and then Cl negative, and then Ar, and then K plus, and then Ca2 plus. So those are like, you know, the combinations. And then they can always change it around here and there. Like they'll pick, okay, this one and this one, or this one and this one, or this one and this one. Like, you know, they can ask you any combination, or maybe they give you 3 or 4 to arrange. But remember, isoelectronic species, the negative ones are the bigger, positive ones are smaller sizes. Okay, so that's sizes. We're done with sizes. We can show you some pictures of ion sizes. So on ion sizes, yeah, let's talk about transition metal. So while we're at here, and in transition metal, if you go down a group, it does get bigger, but along the D block, there's really not a good trend. I mean, I guess it gets smaller and then kind of gets bigger. It's like there's really no good trend there. So you don't want to worry about that. Now, let's take a look at the ions. Let me show you a picture of all the ions. And remember, the cations are generally smaller, right? So the smallest anion is almost the same size as the biggest cations. You see how the radius here? These are the smallest anions there are, and this is the biggest. So they kind of start mixing it over here. So in general, cations is smaller than anions, but we do have some where they start to kind of get about the same size. Okay, so that was slide number 53. Let's go ahead and show you the pictures on the cations and atoms so you can see how pretty they look. So these are the slides right after that, so 50 something. So you see how the cation is so much smaller than the atom because you took off the whole layer on the outside. And then the anions here, they get bigger because of the extra electron repulsion right there. Okay, so that's that. And then we want to look at the next trend now. The next trend we have is called ionization energy. Okay, well, what in the world is ionization energy? So we're on slide 60 right now, and I'm going to show you some trends, and then we'll go ahead and write it out. So ionization energy right here. So the energy required to remove an electron from an atom. That's the first level. Okay, the valence electrons are easiest to remove. When you start removing the core, it's super hard to remove. When it's super hard to remove, you need more energy, and that's the ionization energy, the energy needed to ionize something. Okay, to ionize the gas atom, ionize the plus charge in gas form. So that's the definition of it. We'll write out some stuff to kind of use examples in it. So as you go down a group, the first level ionization energy is just basically taking it from the atom. It decreases as you go down a group, because it's, when you go down a group, it gets bigger. When things are bigger, it's kind of like a big classroom. When things are bigger and the teacher is so far down, like if you have a big auditorium, I used to teach in big auditoriums. So maybe like 200 students, 250, 300 students in a classroom. So when you teach all the way down the auditorium and you come up and you sit at the back row, the last row, the teacher won't realize if you're walking in and out of the classroom. Agree? Whereas if you're a small classroom, like 40 people, I can clearly see who's going in and out. So that's more obvious. So because you are so big when you go down a group, the valence electrons are so far away from the nucleus, they can slip away without being noticed. So when they're so easily lost like that, when electrons are so easy to be lost, the ionization energy is getting smaller and smaller. It's because it's easier and easier to remove it as the further you go down the nucleus, further you go down away from the nucleus. Okay, and if you go across the period, it gets smaller and smaller, so it generally does increase, it gets harder. The smaller it is, the harder it is to ionize. The bigger it is, the easier it is to ionize. So when it's easy to ionize, ionization energy is low. When it's hard to ionize because it's small, it'll be high ionization energy. Okay, so let's write that out. So we want to focus on the first level ionization energy right now. So I like to call it IE, because it's a big mouthful. So energy required to remove one electron from sample or whatever species we're talking about. It could be an atom, could be an ion. The first level is removing it from an atom. Okay, so the first ionization energy is you're removing from an atom. So Al atom, you remove one electron. And when you remove the one electron, you make Al plus. Okay, so that's the first IE, the description. If you remove an electron from an atom. Now I said, as we go, so we're talking just removing the first electron from the atom, okay? As we go across the periodic table from left to right, size is smaller because we explain why Z effective is increasing, right? So it is harder to remove the electron. So IE increases. When it's harder to remove it, the ionization energy increases as we go across the periodic table. Okay? As we go down a group, going down, the size gets bigger. So it is easier to remove electron and IE decreases because it gets easier to take it out. Okay? And why is it bigger? Because Z effective is getting smaller. Size bigger due to smaller Z effective, less pull on the valence electrons. Same thing over here, size is smaller, so Z effective is increasing, so it's harder to pull that, remove the electrons, so it gets ionization energy goes up. Same reasoning here, it has to do with Z effective, but I'm running out of space. So you can just remember it. Okay. I guess I'll go ahead and add it in somewhere. Size is smaller. Over here, Z effective is increasing. Stronger pull on the valence electrons. So we gotta separate these two. Now, okay. All right. So we're talking only the first IE, okay? Which one is bigger? A, AL or S, B, AS or SB, C, N, oh, not NI, it's N, or SI, D, O, or CL. This one here is the one where it's opposing. Oops, sorry about that. Is this my phone is dying? Okay, I better hurry up. Okay. Periodic table right here. O and Cl are opposing trends. Okay, because we say it gets smaller IE and then gets bigger IE. So which one is it, smaller or bigger? You can't tell. So we say we can't tell based on trends. Okay, let's do AL or S. Which one is bigger? Bigger means harder to pull out the electron, okay? AL or S. Which one is harder to pull out the electron? Harder to pull out electron will be sulfur because it's smaller, okay? So it increases. Okay, AS or SB? AS, SB. This one's super easy, right? Because it flips out. Like students can just run out of class without being noticed because the class is bigger. So AS would be harder to remove the electron. So AS would have a higher ionization energy. The harder it is, the higher the ionization, okay? N or SI? N or SI? So nitrogen is smaller for sure, and it's more to the right and up here. So it's going to be nitrogen. That's going to have a higher ionization energy. Okay, so that's ionization energy for the first one. We want to talk about successive ionization energy, okay? So successive means I'm not just talking about the first one now, I'm talking about the next levels as well. So I'll write down equations. So we were talking about aluminum, how aluminum atom, you take out one, you get aluminum plus. So let me show you what the others looks like, okay? Let's go to the next page here. Successive ionization energy, okay? So the first IE we talked about was aluminum going to aluminum plus, and then you lose an electron. And then this is your first ionization reaction. Okay, your second level, IE, is you take the Al, this guy Al plus, take one more out. Now it's 2 plus and another electron. So this is your second ionization reaction. Now we got to go to the third level, third IE of aluminum is Al2 plus from here. Go to Al3 plus. So Al2 plus from the earlier reaction, you go down and take another one out, so you get Al3 plus. And so that's my third ionization reaction. We can keep going. We'll do another one just for fun. Fourth one, IE. For aluminum, you take Al3 plus, and then you go and remove one more electron, and you go Al4 plus. And you're like, I've never seen that. Is that even possible? Well, I'll show you why it's not possible. I mean, I guess you could if you forced it, but it's not natural, okay? So let's take a look at aluminum. It's 3 valence. You take out 1, 2, 3, that's the valence electrons. And you start taking out the fourth one. Try taking an electron away from neon. Neon's like, and no way, I'm full. Why would you want to take my electron away? It's not going to let you. So right here, this fourth level is removing electron from the core, okay? And which is really hard or almost pretty much impossible. So IE is super, super high. It skyrockets, okay? So I'm gonna unbox this one out because this is the level where it starts to go to the core. And then I'll write it out. So successive IE, each level increases. So it increases stepwise with every electron removed. And when it hits the core electrons, the IE skyrockets. So I want to show you some values that they have reported, okay? So we can kind of see every time you hit the core, it does go up like crazy. Right here. So for sodium and for magnesium, sodium is group 1, right? So 1 valence, that one's okay. And then the second one's like, hold on a second, I'm not letting you do that. It went from 496 to 4,000. Like it goes up, up. So it's really hard to remove that core. It skyrocketed because it's now pulling from the core. For magnesium, you have 2 valence. First valence, second valence, and then you're like, oh, it's a core now. It's really, really hard to remove. So that's when it skyrockets, okay? Now, let's take a look at more over here. So you can see clearly on this successive table here, this is slide number 69. You see how it jumps from valence to core and then valence to core, and then this is the valence and that's the core. So the core electrons, once you get to that level, it's really hard. So for group 4, after you remove 4, the 5th one is really hard. For group 5, after you remove 5, the 6th one is really hard. Group 7, group 6, you do 6, and then the 7th one is really hard. Okay, so they kind of show you like as you go up higher. So they show you a trend. They say, here's my trend. First one small, and then bigger, and then bigger, and bigger, and then boom, super big. Then I'll ask you, based on this, what group is this in? Well, you can say, well, it has 4 valence, so it must be in group 4. Okay, so that's the kind of question you'll be expecting to see. So that is successive ionization energy trend. Okay, so that's from the same atom, but just keep removing the electron every time and take another electron from the ion, take another electron from the ion, and that's a successive trend. We also talked about just removing the first layer of electron from the atom. That one's the not successive, but the first ionization energy. We also talked about the trends right there. So the last trend that we want to talk about before we go, I guess we want to talk about electronegativity too. So I'm not going to talk about electron affinity because it doesn't have a good trend. I'll show you what electron affinity means. It's kind of the opposite of ionization energy. Electron affinity is the energy that's released whenever you gain an electron. The more energy it is, the more it likes the electron. But there's no obvious trend here, so we don't want to talk about it. But it's basically the opposite. You know, ionization energy was taking an electron as a product. Electron affinity is putting in an electron as a reactant. Okay, but it doesn't have good trends, so I don't want to use that as a trend. I'll use electronegativity instead. So the trend after that I want to talk about is metallic character. Well, that one's easy. So which side of the periodic table is more metallic? You can tell, well, the side where the metals are. This side is more metallic. The left side is more metallic than the right side, okay? Now, as you go down a group, what makes it more metallic? Metals like to lose electrons. So the bigger it is, the easier it is to lose the electrons, the more metallic it will be. So as you go down a group, it will be more metallic, okay? So the trends here that we have is the first one is really obvious, going across periodic table from left to right, okay? Metallic character decreases because obviously you're going towards the side with non-metals. Okay, and then going down a group, size gets bigger, easier to lose electron, means it's more metallic. Because one of the common signature of a metal is it likes to lose electrons to form cations. So it's more metallic, okay? Size bigger, easy to lose electron, metallic character, more metallic, so metallic character increases. Yes, I technically don't need the more right there. Metallic character increases. Okay, so my question for you, which one is more metallic? SN or TE? And then we have P or SB. We have GE or IN. And then we have the weird one where you can't tell, it's S or BR. So S or BR is S or BR going down and then going to the right. So those are the ones that we say we can't tell based on the trend. Can't tell. Okay, because we don't know their opposing trends, right? But SN or TE, let's look at SN or TE. SN or TE, which one's more metallic? SN, 10, okay? Then we want to do P or SB. P or SB, which one's more metallic? The bigger one is more metallic, okay? SB. And then we want to do GE or IN. Germanium or indium. This is more the middle side and this bigger. So indium is going to be more metallic. Okay, so that's how you can tell metallic character right there. Now, the last one I want to mention, since we're not talking about electron affinity, I want to talk about electronegativity. Okay, electronegativity is how much it loves electrons. So I'll write it out here. Electronegativity. This is going to be the last part. It's technically in chapter 10, but I want to mention it and then we'll pick up on it from chapter 10. Okay, is the ability of an atom to attract electrons to itself. Okay, going across periodic table from left to right. Electronegativity increases. You're like, why is it increasing? Let me show you why. Let's just go over here. F is like, I have one more to perfection. Only one more to perfection. It's going to steal every electron imaginable that passes by. And it's small. So the pull on the nucleus to the outside is really strong. So F is actually the most electronegative thing on the atom, on a periodic table. The opposite is francium. It's the opposite. You're like, oh, I'm really big and I'm a metal. I really want to lose the electron. It's the opposite. Okay. So francium is the least electronegative. Fluorine is the most electronegative. These guys are already full, so they don't care. That's why it's increasing right there. Okay. And then if you have fluorine and oxygen comparing, well, oxygen wants electrons too, but not as desperate as fluorine because it's like one away from perfection. Okay. Now let's go down a group. Going down a group. Size is bigger. Going down a group. Size is getting bigger. So when it's bigger, it's trying to steal the electron, but it's slower because the pull from the nucleus is so far out to the valence layer. It's not going to be able to do it as fast. Okay, so electronegativity decreases. So I want to show you an example here. So if you have F and Cl, both of them love electron, but F can steal it faster. So F is more electronegative because it's smaller, you can pull it faster. So if you go down a group here, F is the fastest, chlorine is second, and then Br, and then I, and then At. Electronegativity. So it goes down, electronegativity decreases. Okay, so that is actually the end of chapter 9 that we want to talk about. I wanted to show you a picture of electronegativity right here. So on your electronegativity chart here on slide number 74, you can actually see there's actual values assigned to it. Okay, so we'll talk more about this in the next chapter, but that's more electronegative right there. Okay, so, and that is the end for now about chapter 9 for periodic trends, and we will pick up on electronegativity in chapter 10.